Hi everyone, this is Slater from Indico. We are going to wait just a couple minutes for folks to filter in and we'll get started in a minute or two. All right, everyone, thanks so much. So we're gonna get started here. Some people might filter in over the next couple of minutes, but we've got a lot of material to get through and not a lot of time. If people have any questions as I go through, I'm going to try to get through the body of the presentation first, but I will have the questions open, so that should be available in case anyone has burning questions, and I'll try to address most of those at the end. So we're here to talk about small data for big problems, very specifically talking about using transfer learning in the NLP domain. Over the last couple of years, transfer learning has become increasingly exciting as a way of using deep learning techniques, but in data regimes where deep learning would typically be intractable. Getting the nuance that you get from these very deep feature representations without requiring really large data volumes, kind of a having your cake and eating it too situation. However, while these techniques have been highly popularized within the image space, they remain experimental in the text space. And specifically when it comes to NLP, it's much newer territory. While transfer learning has seen some really significant successes over the last couple of years, the implementation and sort of integration with the enterprise is still pretty low. So to quickly talk through this, what we're going to go through is, first a little background on me. I'm the CTO over at Indico Data Solutions. I did undergrad in a lot of the research that eventually turned into Indico over at the Olin College of Engineering out here in Boston. Indico generically focuses on automating processes. So any case where you're inside an enterprise and you've got a large volume of documents, some kind of manual human intensive process, and trying to kind of accelerate and augment and partially automate those workflows. And in our day-to-day, we really heavily leverage transfer learning primarily on the NLP side, also leveraging a few of the images, but hopefully we bring some interesting context to this discussion. Our agenda at a very high level is going to be, first and foremost, going through an overview of traditional approaches to feature engineering, just to make sure that people have a base of kind of where we're coming from. an introduction to transfer learning, and very specifically text embeddings, which are kind of the dominant mode of transfer learning in the NLP space, but we'll get into that in some more detail. The distinction between word embeddings and text embeddings. Most organizations today have started looking at word embeddings, which are a good kind of introductory level to transfer learning here. But what we really want to do is give you a sense of how things have progressed, specifically over the last 5 years, and the distinction between word and text embeddings is really centric to that. And finally, leave you with some takeaways and resources. At a very high level, this webinar isn't meant to make you a full expert in transfer learning. Unfortunately, that's not really possible in the course of 30 minutes. What it is meant to do is give you a framing, give you a really good sense of the modern work that's been done in this space and really what's changed over the last couple of years, and give you a few resources to really dig in and start getting good practical experience where you've got time. We are assuming some knowledge in this space, so we're principally orienting this as someone with some data science expertise, but you don't necessarily have to be an expert. We're going to assume that you've got some background in NLP, most importantly, that you just understand what a TF-IDF vector is. I'll make some references to it. If not, it's indicative of keyword-based approaches. Some basic data science knowledge. Most of the models we'll be presenting are based on a logistic regression, just because we really want to center on the transfer learning problem here, and some generic math background. We're going to be talking about vectors. Shouldn't require a huge amount of pre-assumed knowledge, but there will be some pieces that really do rely on these pieces of background. So without kind of further ado, let's get right into it. Really where we want to start is on the problems with text. Right, and what we want to walk through in this first part of the webinar is traditional approaches to featurizing text and how people really go about it. So we've got here on the left what we can assume is a medical record. And in this context, let's say that we've got a series of doctor notes and we're trying to make some diagnosis about this patient downstream, and thinking generically about what we might want to extract in a typical NLP context. So first and foremost, we might want to extract the name. Right, that would kind of be a very immediate and obvious feature, though it might not have a huge amount of algorithmic value. So let's talk quickly about how we would do that. Traditionally, a TF-IDF vector might pick up on this relatively well, just seeing exactly what keywords are present. You know, we'd see names and lines kind of show up pretty frequently. You might run into some issues where names are spelled differently, or there might be variants of the same name. You might use a soundex or a NYSIIS encoding, which are just ways of kind of disambiguating different spellings of last names, sort of different American spellings. Or we might just ignore these, right? Because names might not have the highest amount of algorithmic value, right? We might kind of throw these out altogether. The primary issue that we run into, and granted this is sort of the most straightforward of the features we're going to be looking at, is the out of vocabulary issue. Fundamentally, there are a lot of names. There's a huge amount of variety in last names, especially once you talk about spellings. That's why in this case, a lot of the time people will actually opt to just ignore this data, because solving this for whatever signal might come out of that name is pretty tough. And once you start expanding the vocabulary of your TF-IDF vector out to encapsulate kind of all the possible names, you've got kind of a really massive vector, and you've kind of made all of your other NLP processes a bit more complex as a result. But this is sort of okay. This is maybe the most straightforward kind of feature engineering you would do in an NLP context. Let's move on to the more complex aspects here, right? So John Malkovich plays tennis in Winchester, right? Based on sort of these yellow underlined sections, we know that John Malkovich, we know the gender, we know the particular location where he lives, as well as an approximate age. Right, and this is where we start getting into some of the more complex aspects of feature engineering, especially in a traditional NLP context. You might still use a TF-IDF vector. Again, a TF-IDF vector is kind of the hammer that fits all nails in a traditional NLP context. You might start using some hand-coded features here. Say we believe that gender has particular clinical value. We might put together a system for recognizing these gendered pronouns. And locations might also have some significance, right? When we talk about Winchester in particular, we might start moving towards kind of dictionaries and lexicon-based approaches to attribute kind of specific meanings to those. But as we kind of advance these hand-coded features and lexicons, we introduce sort of a whole series of additional issues. So we run into local context, right? When we start trying to pick up his 60th birthday, right? Recognizing that this is his 60th birthday and not his daughter's 60th birthday, sort of these traditional TF-IDF type approaches won't be able to pick up that local context really effectively. We start thinking about how we would build a gender detection system in here on top of those hand-coded features, disambiguating between a reference to John Malkovich and anyone else that might be referenced in this text actually starts to become really difficult, and gender detection, kind of the naive implementation, is going to be surprisingly brittle. And finally, we can talk about location detection here. And I bring up location only because it's something that you would immediately think, you know, a location dictionary would get us a good chunk of the way there, only to realize that kind of named entity recognition and specifically kind of place detection is still, if not a totally unsolved problem, a problem that still has very, very low accuracy on real world data sets, just because the breadth and expanse of different location names is quite vast. So these are kind of the more critical issues that you start seeing as you start working towards, again, sort of more real world NLP systems. But this isn't even where things get really complicated. We really want to focus on next, which are these blue sections, right? And these are areas that aren't quite so structured, right? Locations and addresses and genders and ages, right, are all things that we can pretty cleanly map to a structured field ahead of time, so that intrinsically makes a problem more tractable. But when we start talking about arbitrary activities, prior afflictions or treatments, or the soreness in the elbow or the steroid shot, or travel information, these may all be really useful when it comes to predicting things in a clinical sense, but modeling these as features and extracting them effectively is just not really straightforward, again, in a traditional NLP context. You're going to go, again, for your TF-IDF because that's always sort of the first reaction, but you really start to see this actually falling apart really heavily. You know, picking up on tennis isn't going to be a great sense of whether or not someone actually plays tennis. Soreness in the elbow and recognizing that those two should be linked because you've got a couple of words in between, you're really not going to pick up with the TF-IDF. So you're going to start relying on things like parse trees, again, getting a bit more complex and a bit more complex, right? We look at the steroid shot, right? Or Casablanca might be a particular location where it might be useful to bring in some domain-specific lexicons if there are particular risks associated with those, and we might know those ahead of time. But you're starting to sense, you know, this is where a lot of kind of traditional NLP projects end up, right? You kind of work through these parse trees, right? You work through these domain-specific lexicons, and as you come up with these additional features that you might want to pull out, you start kind of building hand-engineered systems to kind of pull these all out. At really large data sizes, this can be okay because even if you don't have the most accurate approach, this can sort of fall out in the wash. And some of these more complex aspects like playing tennis, a TF-IDF approach can start to pull out if you've got kind of sufficient n-gram size, if you've got, again, sufficient data. But when you talk about a small data set, there's just no way that you're going to be able to pick up these features kind of robustly. The real issues you're going to run into when you start getting into these more nuanced pieces is this concept of a linguistic context as opposed to local context. So this is semantics and synonyms and things along those lines. You're going to start to realize that especially when you're dealing with real world data, parse trees are not particularly accurate. They make really strong assumptions about exactly how you string a sentence together. And when you're dealing with something that's written not necessarily in perfect English, like a tweet or doctor's notes, these parse trees actually have a very high error rate. And finally, anytime you introduce sort of a dictionary or domain-specific lexicon, you have the issue of maintaining that lexicon, making sure it's up to date, making sure it's sort of appropriately consolidated, which is tremendously expensive and time-consuming. So this is just kind of a brief introduction for a lot of people that work kind of in the NLP space. This is probably a lot of repetition, but to kind of sum up, what we really wanted to do was look at three of the main problems you have doing kind of traditional NLP, especially at low data volumes. And we've kind of consolidated these down to this problem of linguistic context, so having a robust sense of synonyms, different word senses, things along those lines. This local context, where you're exactly figuring out what applies to what in that context, sort of the soreness in the elbow example, and out of vocabulary issues, which are just so common that they're worth mentioning. There's a high level just overview, kind of traditionally how you run into it, really the problems that you typically have. I won't go into this in a huge amount of detail just because we touched on it pretty well in the previous slides, but we'll be sending this out after the presentation, so it's a good kind of summation for that. So let's talk about how we actually solve these problems. again, just to kind of reiterate, we're going to be reflecting back on these three critical problems as we kind of progress through the presentation. So enter embeddings, right? And embeddings, I think it's important to say, are really the primary way in which transfer learning happens in the NLP space. That's not to say it is the only approach to transfer learning, but it's certainly the direction or sort of set of approaches that have garnered the more success and kind of most attention and most active research over the last couple of years. First question being, what is an embedding? Very generically, an embedding is a way of going from our text space. So let's say English, you apply an embedding method. So say word2vec, which is sort of the Coke of embedding methods, if you will, and that it's very popular, but not very good. And then you have an embedding space that you're actually trying to get your text into. So, a 300-dimensional space, or, just to say it another way, you've got this long list of numbers or, sort of an n-dimensional vector. One really important piece here, because I'm sure a lot of people are saying, okay, where exactly is the transfer learning? You're actually training this embedding method, right? So you typically have some method of injecting kind of linguistic context. So you might use a very large public data set like Wikipedia, you might use Common Crawl, you might have a domain-specific data set, right? But somehow you're kind of bringing linguistic context into that embedding method to help it understand how it should be parsing that text space. So again, this is a really high level, but just to make sense of exactly what the set of concerns for an embedding method is and how an embedding works very tactically. So there are a couple of pitfalls. Again, 30 minutes isn't a huge amount of time to go into it. You have to make sure that the data set you train on, the way you add linguistic context, has sufficient and very diverse context, right? Something that you'll commonly run into is if you train this on too small a data set, right? If you don't have a sufficiently broad context, then your embedding method isn't going to be very effective, and you'll oftentimes just end up with really poor performance. Getting clean test train splits is actually surprisingly difficult here. What you need to do at a minimum is actually train your embedding separately than you train your model for whatever downstream task you're doing. So what you really need is kind of two nested cross-validation loops, because you actually do need to do a hyperparameter optimization, both to train the embedding method and then to train whatever model on top of your embeddings you're using for downstream tasks. So it's very important to have a kind of private holdout set. One of the real benefits of transfer learning and kind of using embeddings is that you really reduce the manual feature engineering. Generally speaking, embeddings are very high dimensional spaces. Typical size for an embedding is going to be 300 dimensions. That's not even a particularly big embedding. That's about average. Dealing with anything at high dimensions introduces sort of a unique set of issues, and embeddings play kind of right at that boundary. Things like Euclidean distance, the notions start to change, right? A lot of the assumptions we make about classic distributions start to become very highly inaccurate. Generically, this is called the curse of dimensionality, and the whole topic in and of itself, but kind of worth looking through. And finally, this question of effective benchmarking. When you're wandering into small data sets and you're trying to figure out what is effective at low data, you're dealing with much noisier signals. What we're going to show as the benchmark as we kind of progress through, we actually set up 5 separate runs of 5-fold cross-validation at every one of kind of our data nodes for different data volumes. But benchmarking actually can be deceptively difficult here, just because you've got multiple trade-offs and you're not actually optimizing just one model here, but sort of optimizing the embeddings as well as the model. So just some really high-level pitfalls here before we get into kind of the cool stuff. So again, at a really high level, how do embeddings work? I think that people might be already familiar with this framing, right? This kind of king, queen, man, woman is a really common example here. So the way an embedding works, or rather I should say this is a good conceptual model, and kind of take the vector for king, subtract the vector for man, that resulting vector is going to get you somewhere in the vicinity of royalty, add back in the vector for woman, get somewhere in the vicinity of queen. Because what embeddings allow you to do is that they maintain sort of a geometric structure in this text space. So things like synonyms or holonyms or any of those kind of modes of similarity, right, can be represented as these vector operations. Now, not necessarily in a very clean way, not necessarily in a way that's completely intuitive, but there is sort of a geometric structure, and you're kind of mapping things into this dense space where things have meaning. So you're, again, encoding this meaning in this embedding space, and this vector example is just a good way to think about it. Now, importantly, the individual dimensions are not really human interpretable. So if you ask, what's the x-axis, what's the y-axis on this graph, there's not a great answer that you can give to that. Again, they learn by just looking at generic corpora in most word embedding methods. This is not kind of explicitly supervised, and your goal is really just representing language as accurately as possible in this dense embedding space. So, quick overview on embeddings. So we're going to talk about word embeddings first, because that's sort of the simpler case, and I think what a lot of people might be familiar with. So some examples are word2vec or glove or fast text. These are all word embeddings. I put word in quotes just because these aren't always necessarily on the word level, but again, we'll get into that in a little bit. In practice, what you're going to see when you deal with word embeddings is basically a lookup table. You basically learn an embedding, right? You learn what that vector should be for each of these words using one of these methods on the left. And then in practice, again, you're just looking it up. From training at a really high level here, there's two main methods that you use to train word embeddings. One is called CBAW, or continuous bag of words, where effectively what you're doing is trying to predict this middle word given the context around it. And skipgram is kind of the inverted method of training, where you're trying to predict the context given the initial word. One thing that's a little deceptive here is that you don't actually maintain context in a word embedding context, because it is just this lookup table. So even though this vector is trying to encode as much generic context for the word as possible, you don't actually get any local context here. And obviously the important question is, do they actually work? So here are some benchmarks we've got. This is comparing a TF-IDF approach to glove. On the x-axis here, you've got the number of data points. You can see when you're down at, kind of 100 or sub 100, this is a binary classification task, specifically the movie review sentiment analysis data set. TF-IDF is still noise, right? Honestly, even at 500 data points, you're not doing much better than random chance. Glove, on the other hand, which is generally more effective than word2vec, and is definitely more effective in this particular context, doing significantly better, right? Even at just 50 data points, you're already kind of out of the area of noise. It's pretty accurate. It's not insanely accurate, but you're giving it, again, very, very small data sets. And glove, importantly, is sort of 4-year-old technology. Word2vec, which more people might be familiar with, is even older, which is 6 years old, and things have actually improved really drastically since then. Text really hasn't, right? TF-IDF vectors are still the default, potentially in combination with domain-specific lexicons, and haven't changed really significantly in the past, 15, 20 years, outside of a couple of exceptions. So this is really how you add this linguistic context, right? When you map things into this dense space, because there is this geometric meaning to closeness and similarity, that's a really good way of adding this linguistic context in a kind of implicit way. So now let's talk about local context. So local context, importantly, isn't something that you can actually handle just in a word embedding. You actually need to move to text embeddings. Text embedding, some examples: Doc2vec, Elmo, ULMFit. In practice, this isn't quite as simple as lookup table. So you're just going to effectively call an embedding method on top of some text sample that you give it. And these are often built on top of word embeddings. To give you a sense, again, of the high level training, and then I'll dig in a little bit. If we have something, say, the quick brown fox jumps over the lazy, we're going to have, for this example, assume that we've already got word embeddings computed for each of these. The two most common modes of training are either as a language model, where we're trying to predict that the next word is dog, or as a supervised model, where we just have some true-false type target, and we're trying to change our word embeddings to map to that really well. Those are the two modes, and there's two sort of main classes of models that you use to really work on text embeddings, which are, generically just a way of going from word embeddings and getting more context. So the first is sort of a CNN, or a convolutional neural net style way of leveraging word embeddings, where what you've got is kind of this context window that you see kind of looks at these static windows of context. So you have, the quick brown, and you can layer these on top of each other sort of in a standard convolutional neural net. And then you use that to feed into your prediction. The other style is sort of an RNN style, or a recurrent neural network style, importantly different from a recursive neural net, where what you got is still sort of the embeddings at the start, what you can think of as your output. And then you've got this memory, which is effectively the model's current sense of the sentence at a given time. So at each step, what you're, apologies. At each step, what you're doing is effectively taking your previous memory, the particular word embedding, you have sort of the gate, which are these blocks with the sigmas, that's in charge of combining that as well as kind of the previous states, outputting a new understanding that just gets fed into the next cycle, and so on and so forth. And then after you kind of run through this chain, really reading through sort of left to right, that's handed out to a prediction that you then use to kind of refine this model. So that is really how you add local context, is you want to move to one of these text embedding structures that actually leverages some deep interpretation on top of existing word embeddings. And finally, preventing out of vocabulary issues. The short and kind of the reason that I said that word embeddings aren't always word embeddings, this is just a small excerpt from a recent paper called Fine Tune from OpenAI, where they were actually able to use just byte pair encodings as effectively their coding element here, and actually achieved significant improvements on state of the art in most of the tasks that they kind of worked on. In fact, the use of byte pair encoding, sort of individual words or individual characters, as sort of the level that you're then leveraging into kind of that text embedding framework is become really, really common. And so this kind of power of context means that you can do everything on top of byte pairs, which fundamentally means you no longer have out of vocabulary issues, right? You know, you might not be quite as sharp on things that you haven't seen before, but because you are actually learning meaning on the individual character level, fundamentally you don't have the problem where if you've never seen a word before, your model just kind of falls down flat on its face. So, and again, sort of this question of how much do things improve once we move from kind of this word embedding context to a text embedding context. You'll see here that fine-tuned paper we were talking about, and this is kind of bringing us up to the modern day, if you will. And you see the improvement over GloVe is very, very significant. You know, it takes a little bit of time to learn that extra context because you're combining these word embeddings, so it doesn't outperform until you get to 75, 100, but that's still pretty low data volumes. And you've got very significant improvements by the time you're up to a couple hundred data points. Obviously human analysis isn't perfect, so there's a reasonable question as to whether it's even possible to achieve 100%, but assuming that it is, you're talking approximately 4x error reduction over what you would get on TF-IDF value at these low data volumes. Again, and this is just working on top of byte pair encoding, so very, very low level, very contextual, and again, kind of solving the critical issues you typically have in a traditional NLP context. Just some key takeaways before we kind of switch it over to questions. At low data volumes, embeddings really drastically improve accuracy by using that transfer learning because they're trained on an external data set. Transfer learning moves really quickly. It's important to note, GloVe is not commonly adopted. WorkDevect isn't even commonly adopted, but these are both already kind of out of date. People sort of eye GloVe as something that they might do one day in the future, but sort of the space has already moved forward. And again, this is just a basic framing. This is to help people understand what's happening. There's going to be a longer session where we talk much more about how to apply these and specifically using embeddings in more exotic contexts where you can't just take an embedding, feed it to a logistic regression to get classification. That's going to be the presentation at Data Science Salon in Miami. Finally, some resources, some of the things that we used during this presentation. One is the fine-tuned GitHub library, so that's open source. We have to maintain it, but obviously just free to use to get a good taste of what a real state-of-the-art system looks like here. And so is our benchmarking library that we use to produce all the benchmarks used in this presentation. Just really helps benchmark different embedding techniques more effectively. Sign up for a newsletter anytime there's kind of new papers that come out, new blog posts that people come out that are very good explanations. We try to include it in there, and just always have to recommend the deep learning book. A few really great researchers came together, and it's a good way to just get started with these techniques. So without any ado, any questions kind of available to answer them both here on the webinar, as well as we have an Ask Slater column where you can just ask me any questions and get them handled offline depending on your time constraints. Yep. Yeah. So first question, are the slides available independently? Yes, absolutely. We'll be making all these slides available afterwards, and we're going to send out just a quick note with a link to this to everyone who came today. Yeah, sorry, and just another question about that. Oh, yeah, we've got a question about how exactly word embeddings and text embeddings interact, and how to kind of approximate text embeddings with word embeddings, just because there are better pre-trained versions of word-to-vec and glove available. The short of this, and actually the way that we generated these benchmarks, these glove embeddings are just a mean pool. So you literally just compute the word embeddings for every word, and you then average them together, and you actually get a very strong baseline without having to use anything more complex. Another question, what type of neural nets are the best choice for NLP, and where does the industry move in that respect? This is a good question. I think that when it comes to images, convolutional neural nets are a family that everyone is kind of standardized on. The same thing hasn't exactly happened in the image space. In the text space. In the text space, CNNs and RNNs both have pretty significant advantages. I think that a couple of years ago, people were pretty decided that RNNs were going to be the be-all end-all, if you will. It turns out that you can actually get a lot of context with the CNN approach, and CNNs are probably a little bit more dominant today because they also have a lot of really good computational properties, which are a lot cheaper to compute. It's a hard one to answer. I think that the level of architecture experimentation we're still doing in the NLP space means that while I think the future is going to look more like RNNs than CNNs, there's too much experimentation happening for that. A lot of people are trying to combine these in new and kind of innovative ways. Jeng Wallace was a great paper trying to combine sort of RNNs and CNNs that showed a hint of this. We still don't know how to do it particularly well, though. So good question, tough to give a really definitive answer to that. I have a couple more questions in here. Yep, yeah, so have we had success in industry with applying embeddings? Generally, yes. I think that one of the biggest places where we've seen a lot of success in industry with the use of embeddings is just problems that require very low amounts of data. I think at first, especially people coming from more traditional data science backgrounds, can get a little bit confused when it's not just keywords, right? Keywords are kind of a very straight way of working on things, and a lot of people have very complex lexicons and taxonomies that they built out over the course of years. And I think moving away from those is kind of very uncomfortable for a lot of people. I think that what we found is really successful in kind of driving adoption. Number one is benchmarks, is that people are a lot more comfortable moving to a new system when you can show provably that it actually outperforms their existing system. And importantly, doing sort of a fair apples to apples bake off there. That helps quite a lot. And kind of finally, I think one of the things that really helps get people on board is they don't have to explicitly program every single flow anymore. And the issue of having unknown effects when you change something in your underlying system, removing a word from a lexicon can have kind of untold effects. Changing the weight on something in a lexicon might fix the one example you're looking at, but might break 10 others in your test set. And the other problem is that because these typical sort of feature engineering methods are so kind of manual, you end up with what we often call kind of human overfitting, where because you're looking at the test set, because you're changing your features to reflect that, you actually end up kind of thinking that you're getting much higher accuracy than you are when you're really just kind of implicitly contaminating your training set. And then as far as kind of what part of the industry has the biggest uptake when it comes to these, anyone with really significant document-based processes. So we work primarily in financial services, and there's been a really strong uptake there where they have loan approvals, where they've got appraisal audits, anything where you have a job that is, 80 to 90% kind of rote. Trying to find the parts of that are good automation candidates that are pretty straightforward, but still require some NLP to really understand effectively, and then work to kind of bubble up the 10 to 20% that are more nuanced, more complex to kind of humans. I have a few more questions coming in. Yeah, so just a quick clarification. When we're talking about transfer learning here, talking about using the pre-trained text embeddings for the transfer part, using features someone else created, I'll say generically, yes. It's not a requirement here that you use someone else's pre-trained embeddings. It's much more that kind of the implicit approach to transfer learning here is, and actually here, maybe just go back to this slide. Yep, is this bringing in of linguistic context to your embedding method, right? So whether this is whether you're kind of getting this off the shelf in a pre-made way, or whether you're kind of training word2vec yourself, they're both valid options. They're both transfer learning here. But this is exactly the transfer. You're kind of bringing kind of this linguistic context into your particular problem. Something that's a lot more common in the image space is changing this embedding method a lot more as you sort of learn this text-based embedding, as you actually work on that problem. I think one of the things is that while in theory it's a very good idea, in practice it ends up being a lot less effective than people think. And you actually lose a lot of the really great benefits of embeddings if you're kind of fine-tuning on every pass over. The thing that you have to realize is just sort of a sense of scale, is that this linguistic context down here, you really want to be comfortable. You're talking 10 million to 100 million token data sets, again, at a very, very bare minimum, and that still kind of assumes pretty good distribution of language. So really importantly, you don't want to assume that additional data you add is going to solve real issues in your embedding space, right? When you pass another 100 examples to something that's been trained on 10 million examples, it doesn't have a really big impact. So this is generally what we advise, and from sort of a pre-trained versus training your own, definitely start with pre-trained. There's a lot of kind of non-obvious gotchas when it comes to training these yourself, but absolutely play around with training these yourself. The fine-tune library we link to at the end really does help to give a good middle ground where you can refine the word embeddings, you can refine the text embeddings, and kind of start to play around with kind of training these yourself. Again, because a lot of the test train issues, it's very easy to kind of mess up and get non-obvious test train contamination. So that's actually the primary reason that we don't suggest that you train them by yourself, especially when you're just starting out. Yep. Use case in the legal space, really great question. So yeah, legal space, specifically in financial services, we get a lot of people that are interested. A good way of thinking about this is the reason that low data learning is so critical within the legal space is just there aren't actually that many contracts. So just for instance, and I'm gonna kind of obfuscate names here a little bit, but if you've got a customer that's sort of a large Fortune 500 company, they've probably got somewhere between hundreds and thousands of NDAs that they've signed with other organizations, right? And you can imagine, 5,000 different NDAs is actually a massive volume, right? And you're not going to be much higher than that, even when you're talking about a Fortune 500 company. So kind of a lot of the traditional techniques that you would use in order to, say, pull out the indemnity clauses and identify which indemnity clauses are more or less favorable to your organization, right? A good sort of demo use case is actually very difficult, right? So you really need something that is going to be able to learn exactly what you want to pull out when it comes to extracting an indemnity clause. You have to be able to do that on very low data, as well as kind of what concerns your specific organization has. So you have to do that again, just at a very low data volume. But generically in the legal space, anything where you're sifting through a body of documents, trying to find particular clauses or phrases, trying to kind of interpret those in a way that is likely kind of specific to your organization, those are really, really good framings, and sort of both, I would say contract analysis in some way or another is really the dominant use case in legal that we've seen. Yep, and here's sort of another question. Is it possible nowadays in NLP for companies to solve problems without machine learning, just using conventional NLP techniques? Look, I mean, it's a good question. It depends a lot on the problem. What I will say is that I think that, actually, there's a couple of backup slides here that I'm gonna just quickly refer to. I talked a lot about this manual feature engineering, and it's actually a much bigger issue in sort of this conventional NLP space. So for instance, this is kind of conventional NLP flow, right? Or probably shouldn't be, but it is. You select your features, you optimize some hyperparameters, right? Even if these are just weights on your features, you set up a reasonable test train split, you train your model, you evaluate your errors, you view the test errors, and then you change your features based on that. Well, look at this for a second, because there's a really big problem with this, and it's one a lot of people don't realize. Just like pause for a second. The problem is that you're not allowed to look at your test errors and use that to change how your model is trained, right? If a computer did this, right, is if this were your model training process, it would be immediately obvious this is not appropriate data science flow, right? It means that even if you end up with something that seems to work, it does not actually work, and you're vastly over-reporting your accuracy, right? It means you're overfitting, it means you've got test train contamination, and fundamentally, this is where you get when you do manual feature engineering. So that, I think, is really the primary risk when it comes to using kind of conventional NLP techniques. Because they're so manual, because they are so brittle, right? There's not a good way of developing a conventional NLP technique without sort of adopting this flow. And the problem is, again, when you adopt this flow, your results are not valid, are not accurate. I'm not going to say it is never a good fit, but it is rarely a good fit. And your gut should always be to use a machine learning technique in this space, because then you actually have strong guarantees on how it will perform going forward, which you don't have with conventional NLP. Even though it can be more comfortable to start, it ends up being 9 times out of 10 a really bad choice in the long term. And I think time for probably 2 more questions before we head out. So we've got, what is the image processing part of your company? Oh, okay, yeah, so this is more Indico specific. Yeah, so we do have kind of generic OCR. I'll say OCR is a space where you don't see a huge amount of transfer learning because it's more or less solved. So, using something off the shelf for kind of OCR to get it into a text context like a tesseract or using Abby or something like that is generally what we would advise. But then fundamentally, in terms of sort of what we do, is because we do focus really heavily on transfer learning, we have sort of a more traditional transfer learning option for images. So classification, it's really useful for a lot of downstream processes like splitting up pages, OCRing them, and then handling pages that are formatted differently, trying to extract different fields and things along those lines. So, fundamentally, we find that a lot of document tasks, when you're kind of sifting through the contract, actually end up being image tasks, just because the formatting of an image in a document has a lot of non-obvious information. And then last question before we kind of wrap up. Have we seen success with hierarchical embeddings? Someone asked this is a very good question. Yeah, and asking specifically if these outperform traditional embedding methods. Yeah, so we have played around with hierarchical embeddings. There's a lot of different ways of kind of approaching this. I think the most common one, and sort of the most common assumption here, I can't say specifically to this question, is the sense of word senses, right? This idea of, hey, in WordNet, you have kind of traditional synsets that have this notion kind of very strongly built in that says, hey, we're going to learn sort of a generic embedding for, let's say, the word mouse, and then have kind of within that 2 different word sense embeddings for a computer mouse and sort of an animal mouse. Yeah, so the short is there have not been, to my knowledge, papers that show really successful benchmarks on top of hierarchical embeddings. It's tough to get right. I'll say that fundamentally the embeddings that we learn are learned and kind of applied hierarchically when you put them in sort of a traditional deep convolution or deep recurring kind of framework. And obviously those are very helpful, and kind of adding depth in that feature engineering has helped quite a lot. As far as I can tell, and I'll say this is an opinion at this point, not something that I think there's been really sufficient literature for me to put a foot in the ground. But I think the assessment that hierarchical embeddings are the way that information is conveyed when there's ambiguous meaning within words is maybe not quite correct. What I've seen much more is that actually the structure of the embedding space, I can just go back to that quickly, but the structure of the embedding space seems to actually have a much larger impact. So it's much less about kind of learning hierarchical embeddings. Again, I can't say definitively, but there hasn't been a lot of success that we've seen there, or that I've seen reported there. But where we have seen a lot of success, and where I have seen a lot of really interesting papers and a lot of really interesting work, is places where you're making less obvious assumptions about your embedding space, right? Basically anything where you stop treating it just as Euclidean space, stop assuming that Euclidean distance is actually meaningful. A lot of really interesting sort of meaningful improvements, like a word movers distance, the UMAP paper that recently came out that gets a much better sort of manifold layout on top of these embeddings, have all used that approach. potentially as an alternative to hierarchical embeddings. I apologize if I misinterpreted that question. It's a really interesting one, but that's kind of the high level, but a very active area of research. It's not one that I can definitively say like isn't a good idea, other than we haven't seen particular success with it. Okay, great. Thanks so much, everyone, for attending. We're going to wrap up now. We'll send the slides around afterwards. And again, if you have any other questions that we didn't have time to get through, please just send them along to the Slater Ask Core. Thanks so much, everyone.